Who are you?
I'm Matt Lish, and I'm a chemist and nuclear engineer with Flibe Energy. A recent physics graduate who came to work for Flibe Energy, I taught him reactor dynamics, which fundamentally doesn't change a whole lot based upon whatever kind of reactor you're designing. The modeling approach is the same. The way that we facilitated that training, we worked together to model an old Oak Ridge design, the 4528, the two-fluid breeder reactor designed at Oak Ridge. It shares a lot of very similar characteristics to the lifter because they operate on the same fundamental principles. We worked together to build a dynamic model of that reactor. And then we presented the results of that research to Kirk. And Kirk offered me a job. I had never been exposed to molten-salt reactors. I learned about this entirely new concept of a fluid-fueled reactor. And all of the difficulties that I learned about while modeling the light water reactor for my graduate work, it was part of an interdisciplinary team that was essentially doing a conceptual design of a reactor that was very similar to other reactors. But I got to see what that whole team worked on and all the different challenges that people had to work through, as a lot of it driven by the fact that it's a high pressure system. Pressurized water reactors operate at 200 times atmospheric pressure. And then I turn around and I get this project to go model this system. And the first thing I do as I'm reviewing this design document is I'm looking at the pressures that are in the primary coolant loop. And I'm going like, okay, well, you're telling me that inside the reactor itself, where the nuclear process is happening, this is like 1.5 atmospheres. and that's relative to outside. You know, we're barely above the pressure outside of the vessel. Well, okay. That's awesome, because that means I could take the lid off of this thing and watch it. I mean, not really, because there'd be too much radiation, but from a point of view of nothing's going to fly up at me. And then when Kirk offered me a job to come work on actually designing that reactor and driving that class of reactors forward, I was thrilled. The chemistry of a liquid fuel is incredibly important to how that system operates. And that's why the lifter has a chemical processing plant that is part of the reactor cell system.
Do you guys still typically call it lifter?
We talk about molten-salt reactors generally.
Yeah.
And then, the lifter is a specific design.
So what characteristics make lifter?
The chemistry of a liquid fuel is incredibly important to how that system operates. And that's why the lifter has a chemical processing plant that is part of the reactor cell system.
How did you end up becoming a nuclear engineer? Chemist and or nuclear engineer?
Chemistry I just really enjoyed in high school, and so I chose that as a major in college. The PhD chemists that I knew at that time mostly worked in the pharmaceutical industry. And I wasn't particularly drawn to that. I was really interested in energy because as a student of history, I've observed that with the price of power goes the development of civilization. As you progress from using a horse to plow a field to a tractor to plow a field, you have a massive change in the amount of people you can feed with the effort of one farmer. So that means you can have more people focused on things besides growing food for themselves to eat. The more people that are focused on things besides the necessities of life, the faster we advance technology, the faster we advance civilization. You don't have a lot of options. You pretty much have fossil fuels, and then you have a limited amount of hydro that you can do with rivers. And then you have wind power, you have solar power, you have nuclear power. And there's a little bit of geothermal that you can do, but that's very regionally dependent. Just like hydroelectric is regionally dependent based on where you have rivers, where you can build dams. And every form of energy generation has environmental impact. When I'm looking at nuclear power, I see something that is, as we currently use it, a well-developed technology that is remarkably safe, and it's also reliable and dense and compact by comparison to, for example, a solar field that can create a gigawatt of electricity takes up a lot more space than a nuclear power plant that creates a gigawatt of electricity. So I decided to go to graduate school for nuclear engineering. That was just a couple of years after Fukushima. Before I made the decision to go for nuclear engineering, I said, hey, is this an existential threat? Are we going to not do nuclear anymore because of this accident? And their opinion was that it was a bump in the road, a big bump in the road, but ultimately just a bump in the road.
Nuclear folk, or was that opinion of like utility folk?
Utility folk. So I went off to school and we started closing reactors. And I did almost all of my graduate work on light water reactors because that was the work that was funded. So this is low order modeling of the dynamic response of a reactor to some change, whether it's a change in the flow rate of the coolant or a control rod moving in the reactor. You're modeling the response to a perturbation in the reactivity. So that project was for a large integral light water reactor. But the idea being that the primary coolant water that is circulating past the nuclear fuel in the core never leaves that primary containment. It's called an integral reactor because you don't have a pipe running from the primary reactor vessel over to a steam generator like you do in a traditional PWR, like the ones that we have all over the country and the world today. The reason that that is a desirable design feature is that it eliminates the possibility that that pipe can have what's called a double-ended guillotine break, which is where you imagine a guillotine going through a pipe and now you have a completely open pipe and water is coming out. It's the maximum flow rate at which you can lose water from the primary reactor vessel. If you eliminate all of those pipes, you eliminate that entire class of design basis accidents. So it was seen as a design feature that would allow for improved safety in the reactor.
So you're modeling like an integral pressurized water reactor.
But a big one.
A big one. And is that design category that ever was commercialized? Do those exist in the real world?
Not big ones. The commercialization of integral PWRs is currently underway by NuScale. At the small scale, because at the small scale you can achieve natural circulation. And then they get a whole host of passive safety benefits from that is really a building block, especially from a regulatory point of view. It's a building block for advanced reactors. So advanced reactors are all coming along here, and we want to be able to license our designs. The regulator's job is to make sure that the public and the environment are kept safe. Just like the FDA regulates medications to make sure that there's not some willy-nilly new medicine on the market that kills people. You know, the NRC's job is to make sure that people out there making commercial nuclear power aren't hurting the environment, first and foremost, aren't hurting the public. But when you're coming to this regulator with an entirely new technology concept, there's a lot of education back and forth that has to take place so that we can ultimately arrive at a safe, licensed, operating nuclear power plant.
And you're saying education of the regulator?
The regulator has to educate themselves about the new technology. And oftentimes what that involves is then developing new regulations, new rules based around their understanding of the technology. Because a lot of the rules that are in place are very specific and uniquely applicable to light water reactors. They describe things about the fuel pin. Well, if you have a liquid fuel, you don't have a fuel pin. The companies developing advanced reactor designs are working with not only the Department of Energy, which does a lot of really foundational research to support the development of these technologies, but also with the regulators to ensure that we arrive at a situation where these reactors can actually be effectively and safely built and operated. In focusing on the chemical processing system, I quickly started diving back into my roots as a chemist from undergrad, because if you don't have any training in chemistry, it takes a lot more study to understand a lot of the processes that are taking place. But the more that you have a background in chemistry, the faster you can come to understand how these processes are designed to work. And then you start to find yourself asking questions about, well, how do I know it's going to work that way? And what do I need to test to figure out how it's going to work? And then you go talk to experts at a national lab and find out that you only have the tip of the iceberg of the questions that need to be answered, because that's always the way it is when you go from, hey, I'm a novice and I'm just reading a couple of papers, to, hey, I'm talking to an expert that spent 40 years doing this kind of chemistry. And that's what led us to the project that we have going with Pacific Northwest National Lab. So we started talking to people about the fluorination process, because this is a critical step in the chemical processing system. The chemical processing system's job is to keep the reactor fueled online and to keep the fission products that grow into the salt that would interfere with reactor operation, to remove those, so that you can lengthen the amount of time that you have to go before your reactor physics forces you to shut down or replace components or something like that. Everything that we're doing in this design is trying to optimize that reliability of operation and safety of operation. So we clean the salt continuously online to remove things that would either interfere with safe operation, like xenon. Xenon is something that can create unsafe transient conditions in a reactor. Xenon was a critical component of what happened at Chernobyl. And xenon is the reason that modern, even though they're incredibly safe and have none of the safety vulnerabilities that Chernobyl and similar reactors, RBMK reactors, have, modern PWRs still have a limitation in how they can operate because of the fact that they can't remove xenon from their fuel, because it's a solid fuel and the xenon's trapped inside of it. If you can remove xenon, your safe reactor operations become more flexible. And that's what allows a liquid fluoride thorium reactor to follow the demand of electricity on the grid in a very dynamic fashion. You can turn down the power, and all you have to do that is decrease the amount of energy you're taking out of the reaction system. And the reactor will naturally decrease in power. And so it'll go down in power, and then you can rapidly bring it back up in power. You can't do that if you have xenon trapped inside your fuel.
We do have other molten salt reactor companies saying they're going to load follow too, right? So you have the fast spectrum where xenon's not going to really absorb the neutrons, and I guess it's not going to play the same role. But aren't they converter reactors also able to load follow, or are they not able to load follow in the same extent? Or how?
They should be able to load follow. I'm not aware of anything. I haven't modeled them, so I don't know how quickly they can load follow. But I'm not aware of any fundamental physics that would prevent those reactors from also performing quite well in a load following environment.
You get rid of the xenon, it lets you load follow. Is that the going up part or the coming down part? Like what's the...
It's the going up part.
Okay.
So just a little bit about it is that xenon absorbs neutrons. And if you're at low power, you don't have a lot of neutrons. If you're at high power, you have a lot more neutrons. Your neutron balance at low power and high power is the same, because your reactor is fundamentally critical. It means that you're creating enough neutrons as you are absorbing so that the number of neutrons that you create with fission is balanced by the number of neutrons that are either lost from the system or that are absorbed and create new fissions. The total population of neutrons is much smaller at low power than at high power, obviously, because there's much less fissions happening. If you have been operating at high power, then you have been forming fission products at a certain rate associated with the number of fissions that are taking place. And the amount of xenon that you're forming is just, on average, it is statistical percentage of the number of fissions. If you go down to low power, this xenon is there. It hasn't absorbed neutrons and been converted into something else yet. So you've just dropped down to low power and you have a whole bunch of neutron absorber. So your neutron population has shrunk, but the amount of absorber is the same as it was when you were at a larger power level. And so you have to wait for that xenon to decay. It has to decay away before you can safely bring power up. Because if you bring power up quickly, when you have all that xenon, what's going to happen is you're going to not be able to get the power level to rise. So if you're withdrawing your control rods because you're trying to get power to come up and it's not coming up, so you keep withdrawing them more, then what happens is that you have built up this sort of deficit of excess reactivity that is not excess compared to the xenon, but it is excess if the xenon were not there.
The xenon's going away.
And then the xenon goes away by neutron absorption and by decay. And so suddenly you're stuck at some low power level and you were trying to come up a little bit at a time, and then you have way too little absorber in the core when that xenon absorber disappears and you're supercritical. And then you have a massive power transient. And your system either survives it or it doesn't. In the case of Chernobyl, the system did not survive the power transient.
When you're looking at removing xenon, does that even tap your skills as a chemist, or are you just like, that bubbles out, whatever? It's not. I mean, is there any challenging aspect to that at all?
I don't know that there's necessarily a challenging aspect to xenon removal, but there is a lot of very interesting chemistry associated with how we treat that off gas. Because this is a gas coming out of your system. You got to do something with it. You can't just let it go into the atmosphere. You can't just say, here, stick a cork in the reactor, and oh look, the pressure's getting high. Let's let some xenon out.
Yeah.
That's not something you can do. So you have to. It's an off gas stream, and it has to be managed. And it contains xenon, and it contains krypton, and it contains tritium, and the gas that you're sparging through there is helium. And you could also have other things entrained in that gas. Well, you can just imagine if you're bubbling a gas through liquid, and you're bubbling it pretty fast, there's a lot of froth coming up, right? Mm-hmm. Well, there's also liquid coming out of the top. And if you have solid particles in there as well, they can become attached to some bubble that finds its way outside of your liquid state. So you get solid particle depositions. There are metals that don't like to be dissolved in the salt, and they will come out and end up in your off-gas system. And so you have to have a mechanism for handling that to make sure that they don't end up clogging up your off-gas system. Kind of like plaque in an artery. It might not be something that happens for 40 years, but it's something you have to be thinking about and prepared for and understand what's going to happen so that you understand how your system performs.
You're saying you didn't really go back to your chemistry until you started with the molten-salt reactor. Are there any analogs for this with PWR? Like, what's the closest thing to a chemistry challenge with a PWR?
Well, I know that PWRs do have very careful control of the chemistry of the water. I haven't worked on that. I think I took one class in graduate school about chemistry management in light water reactors. So I'm definitely not an authority on the subject, but I know that they have to have very pure water. Water chemistry is managed a little bit differently in boiling water reactors from pressurized water reactors. It's a matter of balancing the burnable poison boron. So they put hydroboric acid in there in order to manage the fuel cycle. It's a fuel cycle management technique. And boron absorbs neutrons, but then it is converted to something else that doesn't absorb neutrons as effectively as the boron does. And so it's called a burnable poison. It's a poison because it absorbs neutrons, so it poisons the fission reaction. But it's a burnable poison because it goes away when it absorbs a neutron. It stops being the poison that it was.
So no one came up with a better term for that?
That's the term we use.
LFTR is killing me for some of these words.
Yeah. Well, the lifter doesn't use burnable poisons.
There you go.
There's chemistry there, and I know that they use lithium hydroxide in there as to balance the pH of the water because you've added hydroboric acid for reactivity control, and now you've added lithium hydroxide. And I know that there is a water chemistry management system, essentially a water plant, that is adjusting, it's measuring and adjusting those species and probably other species in order to manage the pH, which is how corrosive, what the oxidation potential of that water is. And that's really important because if that water gets too corrosive, it will eat the fuel cladding around the solid fuel, which is made out of a zirconium alloy in most cases. We do a really good job with light water reactor safety. I don't want to be confused to say that there's anything unsafe about light water reactors today. Light water reactors today do not perform economically, and they only do one thing, and that's make electricity. There is chemistry, pretty sophisticated chemistry involved in how we manage light water reactors. I've just never worked on it.
Okay, let me bring up the concerns I see online, and it usually has people pointing out there's radioactive materials in the salts, and they question whether or not the kidney can be maintained over time as you're using it to perform online purification.
Sure. You could think about the salt, because it's got fuel dissolved in it, over time, it has the same thermal energy generation and radiation generation as spent nuclear fuel from light water reactors. Because it's the same process that's happening. You've got fission happening, you're making fission products. Fission products are the source of the high doses of gamma radiation that are present in the chemical processing system. High doses of neutron and gamma radiation present lots of challenges for electronics that make it difficult to have the kinds of equipment that we might like to use to operate a system in that space. For example, it's very convenient if I want to look at something to have a video camera. But if I take your iPhone and I put it inside the chemical processing plant of a lifter, it's not going to last very long. And the Wi-Fi antenna is probably going to go first. So it's not going to be a reliable means of observing your system. But there are technologies around today, and there is a lot of very valuable work being done, both at the national labs and in the private sector, to develop technologies that can survive in that environment for long periods of time and provide the kind of information we need to run that system. And the oldest example in the book is the thermocouple. It's been around forever. It's what they used all over the MSRE. They had it instrumented with hundreds of thermocouples to measure temperature in lots of places. Temperature is one of the most important parameters you have to measure when you're controlling a nuclear reactor. Another important parameter to measure is pressure, because as fluids move through structures, they lose pressure. The change in pressure across something like, say, a heat exchanger is an excellent indicator of how quickly that fluid is moving. Very straightforward to develop calibrations for that. I simply pump the fluid at a bunch of different flow rates and measure the change in pressure across that structure. And now I have a very accurate correlation for what the flow rate is. And the reason that's important is that the fundamental basis that we use for defining the power, the thermal energy that's coming out of a nuclear reactor, is based upon the change in temperature across wherever it's being heated up, which is the reactor core, times the flow rate, times the heat capacity, which is a measurement of how much energy the fluid can absorb for a certain mass to change in temperature by 1 degree. Those three numbers, the change in temperature, multiplied by the heat capacity, multiplied by the flow rate, tells me watts of energy, how many joules per second are coming out of that system. And that's sort of the definition of your power. And power is very important because power is what you're licensed to operate at a certain power level. Oh. And so if you are not operating at that power level, if you do not have a high degree of certainty based upon your instrumentation that you're operating at that power level, then you have to decrease in power in order to be sure that you are not operating above the power level that you are licensed to operate at. Every time you have to drop in power, you are losing out on sales of electricity. I've been told before by people that if an engineer working for a power company that operates a nuclear power plant comes up with something in the course of their career that allows that reactor to operate at 1% higher power, they've paid for their career and 10 other people's, because of the amount of extra revenue that generates from the sale of electricity over the lifetime of that plant. From an economic point of view of operating reactors, it's very important to have good instrumentation readings and to not have a lot of uncertainty in them. Because if you have a lot of uncertainty, the only way to accommodate for that uncertainty is to decrease the power. We have very good approaches to measuring temperature and pressure inside of high radiation environments. That's established technology. So the fundamental instruments needed to control the reactor are there. The neutron detectors needed to control the reactor, established technology. Then we go over to the chemical processing side and we say, well, how am I going to control that piece of equipment? Well, what do I need there? I need motor-operated valves and I need motor-operated pumps. And the only aspect of those two pieces of equipment that doesn't like radiation is the motor. Thankfully, the valve operating element or the pump operating element can be controlled by a motor with a very long shaft, which means I can put a whole lot of concrete in between the motor and the part of it that's actually moving the salt, which is in the pump head. And all that concrete shields all that radiation and protects the motor from the dose. So that's the most basic way of having any piece of equipment operate. If you have something that's sensitive to radiation, like you or me or the camera, you have to follow the basic rules of radiation shielding, which are time, you minimize. If you have to put something sensitive to radiation near a source of radiation, you minimize the amount of time that it's there. You increase the distance that you are away from the radiation source, and you increase the amount of shielding that you place in between the sensitive item and the source of radiation. So in the case of the pump and the motor and the salt, you have a bunch of concrete between the motor and the pump, and you've shielded the motor so that it's not subject to that dose and it has a useful lifetime. If I want to understand the condition of my salt, I would look towards the promising technology that's being developed in optical spectroscopy. If I can get a probe that will send light into my salt and receive light back out of that salt, I can connect the sensitive electronics, which are going to interpret that data, to that probe with a fiber optic cable. And that fiber optic cable can be quite long so that I can get the necessary shielding and separation I need so that those electronics are safe. Fiber optic cable itself is sufficiently resistant to radiation damage by gamma radiation that it can have a useful lifetime in that environment. Of course, no mechanical process system runs forever. Everything has to be replaced. You're always going to have to do maintenance. So you have to have a viable strategy to accommodate, well, what happens when a pump fails? At some point, something's going to break, a seal, an impeller is going to crack off. You're going to have something go wrong. You have to replace that pump. You have to develop a remote handling technology for doing that. But this is not news to the molten-salt reactor community. In fact, there is a video already out there on YouTube that was made. Wasn't made, YouTube didn't exist at the time, but it was made by the Molten-Salt Reactor program here at Oak Ridge. And this video goes through how they used an entirely remote manipulation system to replace components within the primary loop of the molten-salt reactor experiment. And they didn't operate this technology on the molten-salt reactor experiment itself. They operated it on a mock-up. They were showing how they were going to do it. But they created something that would actually work on the real stuff. And this was with 1960s technology and robotics.
I've heard people say, when I said I was so excited the molten-salt reactor experiment video came out when they dug that up, and then the other one came out, the maintenance one. Mm-hmm. And I was like, isn't it great to get the molten-salt reactor video? And people were like, oh, it's the maintenance one. I mean, most people are more interested in the maintenance one.
Well, if they understand where the challenges are, yes, because maintenance is a big challenge. But the idea that it's a showstopper just kind of falls flat the moment you watch that video, because it shows that there are very tractable methods for having mechanical systems that are distance separated. Most people today, when we think about robotics, we assume there's a lot of electronics inside of those. But if you look at the way a hot cell operates, which is a research environment that allows a person to stand outside of a bunch of shielding and then use a pair of manipulated arms that they control outside of the cell, and inside of the cell, there's what are essentially robotic arms that are manipulating things inside the cell, but there's no electronics involved. It's all mechanical. It's all cables and pulleys. And you can take that exact same approach that we've used to do research on radioactive materials for decades and apply it to a larger system where you have to have motors outside of the radioactive environment that are providing the necessary energy to control the mechanical arms inside of the radioactive environment. And we can do a heck of a lot better with our modern control technology and our modern electronics outside of the radioactive environment than they could do then. Then I would probably also comment that there is the potential to actually have integrated circuits in a high radioactive environment. Now, this has never been demonstrated, but when we talk about why electronics fail under a high gamma dose, it's predominantly because silicon fails under a high gamma dose. And silicon is the semiconductor that underlies most of our electronics. There's another semiconductor that has very good semiconductor performance, and it's called uranium dioxide.
I didn't see that coming.
Uranium, yeah, look up uranium dioxide semiconductor. You will find there have been numerous studies that have examined the performance of uranium dioxide as a semiconductor. What I haven't been able to find is people who have actually built computers with it. And my only assumption about why is that there hasn't really been a huge need. Most of the papers that talk about uranium as a semiconductor talk about its potential for application in space systems, because that's where there's a market. There's not a whole bunch of people building molten salt reactors that need electronics to go inside of them right now. So because of that, we don't necessarily have a market demand for someone to go out and build a uranium dioxide chip for a computer. But if you did that research, you could probably start building integrated circuits with uranium dioxide as a semiconductor. So you could potentially have signal processing equipment much closer to the sensing element.
If you see, is it time you got to grab?
Oh, it's 2:00. Yeah, I should.
Okay, thanks a lot.
Yeah.
Maybe I'll try get you a soundbite later, but
Sure.
Thank you so much.